Welcome to session ARC346, scaling to 25 billion daily requests within 3 months. My name is Jagmeet Chawla, and I'm Chief Architect with the Weather Channel. I also have Raul Frias with me, who's Solution Architect for AWS. So what do we expect from this session? We are going to be talking about our experience, Weather Channel's experience, building a big data distribution platform. We'll start out with the goals, what the goals were for that platform. Then we'll take a deep dive into architecture, both logical as well as physical. We'll also talk about data supply chain, from ingest all the way to the distribution. Then we'll talk about our journey. How did we scale to those 25 billion requests per day? Then I'll hand it over to Raul to provide some AWS insights. And finally, we'll wrap it up with the evolution of the architecture. So before we actually jump into the platform itself, let me give you a background of the Weather Channel or the Weather company itself. The company here, the technical team has done an awesome job building a state-of-the-art big data distribution platform. And let's start with the problem statement itself. And for that, I would like to show you a video. That's so awesome, isn't it? Imagine the problem statement for a minute. What we are trying to achieve here. We are trying to map the atmosphere of the Earth, not just in 2 dimensions of latitude, longitude, but also 3rd dimension of those 62 miles of elevation, because that happens to be very important for weather. And then there is a 4th dimension itself, time, because the data that we are dealing with is extremely volatile, and it changes very rapidly. Imagine the amount of data involved in this effort. And then on top of that, we have to apply all the cool weather science to it, forecast models and all those things. And finally, we have to take the information out of it, and we have to distribute it out via billions and billions of API requests. That's the platform we are going to talk about. So to summarize, we are the weather company. That's where word comes to get its weather information. And we have various channels of distribution. Of course, we have the Weather Channel itself, which is the #1 most distributed cable network for weather. But then we have the digital properties, weather.com, wonderground.com, 125 million monthly uniques and counting. And then we have some of the top mobile apps on iOS and Android. 170 million app downloads and counting. All in all, we reach 158 million unduplicated consumers. But even if you don't use these platforms, these digital properties or the apps, chances are that you consume our data. because we power weather for Apple, Facebook, Google, Microsoft, and quite a few other companies. And then we have a B2B division, WSI, that has 4,600 plus customers across 60 countries in various industry verticals. So how do we do it? Actually, at our heart, we are simply a data company that simply happen to specialize in one type of data, which is weather. We are a data company. So we start out with ingesting terabytes and terabytes of data per day from various different sources, 800 sources of ingest, 20 terabytes data ingested daily. Data from, for example, network of weather sensors, 100K weather sensors or more, global lightning detection network, radar, location, satellites, planes, and then we have some of the largest collection of weather data itself, observations and forecasts from various agencies, government and non-government. We take all this data, and then we actually apply state-of-the-science forecast technologies, forecast models, some of the best industry forecast models that we have. We apply proprietary radar algorithms for visualization. We do weather analytics on that. All of this backed by more than 200 full-time meteorologists on staff. We do human over the loop as well. We also produce a lot of weather-related content, video, images, articles, all those in-house. And then we take all this information that we have produced, and then we expose it out to the world via our weather and content APIs. And that's the platform that distributes those 40 billion API requests daily. So what about the data itself? All right, we have weather data, observations, forecasts, radar, alerts, notices, emergency bulletins. We have all that. We also have health and lifestyle data, data like pollen, ski resorts information, and all that information. And then we talked about content, articles, images, slideshows, videos, maps, all of that information. We also ingest a lot of domain-specific data from industry verticals like aviation, energy, and insurance. So we get data from those as well. So this is a cliche slide, 3 Vs, but every big data presentation needs one, so here it is. So we talked about the volume, 800 plus partners, 50 gigabyte of raw compressed data per hour that's flowing through our ingest pipeline. And then for distribution, several billion requests per day. So we got the volume. We have that locked. But all the data that we saw on the last slide, we get in a variety of different formats. We get those in proprietary, open, textual, structured, unstructured, binary, pictures, images, videos, GRIB2. If you can think a format, chances are that we have it. So we got the variety as well. And then how does the data arrive to us? We do both push and pull. Data is either pushed to us or we go and pull it from the sources at varying frequencies, and sometimes as short as every 5 minutes. But a lot of our data, if you think about the weather, it's very event-driven. It's alerts and notifications. So as an event happens, a severe weather, a flash flood, a lightning, we get notified. We get alerts for those things. Because we are dealing with some of the world's most volatile atmospheric data, we have, due to the severity of certain events, very short time to prepare it. Sometimes as brief as 50 to 20 seconds to prepare and serve. So we got the velocity as well. So we have the 3 V's cover, and hence big data. Okay, so what about the distribution, the other side of it? Once the information is prepared and ready to be served, all these channels that we talked about earlier, digital properties, mobile apps, Apple, Google of the world, all these, our partnerships, and B2B, we serve them all via our API platform. That's what we initially talked about when we actually started building it. We were targeting 25 billion API requests per day. Now we are more than 40 billion API requests per day, and we expect it to go to 60 billion per day by end of year 2015. So how are we doing it? This is before the cloud in the dark ages, about 3 years back. This is how we were doing it. We didn't even have an on-demand forecast system. We just couldn't do it. We had a batch-based forecast system that will essentially compute the forecast, write it to a database, and from there it is going to be replicated out. That's how we were doing it. We had a Java-based monolithic applications or a set of monolithic applications targeted for things like big web, mobile web, and data services as well. We were calling those clean factories, all backed by homegrown CMS and run from TWC data center. The net result was the next two things that you see. One, we were slow in time to market for any new product and content. The time was measured in months. And we were also limited in terms of distributed scaling due to limitation of our data centers. So we set out to fix all that and reboot and reimagine our entire technical stack. And what were our goals there? From a business perspective, business wanted an extremely low latency, on-demand forecast system. No more batch forecasting. So that was the key, an on-demand forecasting system. Then we wanted to take all that data, and we wanted to distribute it out to billions and billions of requests that will come our way, so highly scalable distribution platform. Then we wanted to reboot our entire digital stack, our digital properties, weather.com, mobile apps, and CMS and all those, to actually leverage this entire stack that we were going to build. Main objective there, reduce time to deploy the new data sets from months to weeks. And we also started to see that data distribution platform itself as product. So we wanted to expose exact same APIs that we were going to use to our partners for getting the weather data, which means we needed a secured and metered access to those APIs. And while doing all this, the requirement was also to consolidate all the data centers. So mapping those business goals to technical strategy, this is what we came up with. We wanted a 100% cloud-based solution that's capable of ingesting and processing those terabytes of data, but also handling billions of requests per day, so both ingest as well as distribution. We were targeting extremely low latency APIs, 25 to 100 milliseconds. Early in the game, somebody actually came up with this number, 25 milliseconds, and that got stuck. We were also, of course, looking for a highly scalable and a highly available system, 4 nines. That's what we were targeting. In order for us to reduce time to deploy new data sets, we needed a very sophisticated generic data processing engine, and you will see that. That's the foundation of our stack. So we were targeting generic data processing engine, DPE. Of course, for APIs, we were targeting developer-friendly APIs, and all backed with authentication, metering, and throttling. So how did we do it? What was our architectural blueprint? What was the plan? Looks something like this. Like I mentioned earlier, at the bottom, the foundation of this entire stack is this data processing engine. Then the next layer on top of this is the storage layer, and also sitting on right is systems of record. The reason being, sometimes you cannot just store that. There are always going to be systems within your technical stack that are really good at doing its job and doing its job very well. Example in our case is forecast on demand system. It has a lot of meteorological science, weather science in it, and that's what it does. It does its job really well. It's a C++ based in-house custom system that takes a lot of data, and actually it produces a forecast out of it. So that would be an example of system of record. So sometimes data processing engine needs to take all that data and gives it to those systems of record, and then they will produce their end result from there. Layered on top of it is data services. So every API request comes through that data services. Never hits those systems of record directly. That's going to be responsible for distribution. It's going to be responsible for scaling. It's going to be responsible for caching. It's going to be responsible for everything from a distribution perspective. Gateway or API gateway is responsible for routing, metering, throttling, those kind of things. And of course, we need CDN from an edge perspective, caching as well as compute. So why did we design it this way? We knew it was an extremely large undertaking, so we have to do a divide and conquer approach. We designed our layers decoupled or loosely coupled so that different teams who are focusing on developing these layers can do their job and do their job really well. Not only that, they can work on an independent delivery timeline, but they can also pick best tools and technologies for the job. So I gave an example of forecast on demand system. It's a C++ system, but another system of record, for example, is Drupal, and that's a PHP-based system. Data processing engine is written in Java. Data services are written in Java and Scala both. So we wanted to give these teams flexibility to pick the best technology that is suitable for what they are doing. The only thing that we did between these layers is we standardized on RESTful APIs over HTTP as our interface. Essentially, we were building this data platform, which just happens to serve weather data as service. OK, so let's jump into this, starting with the foundation itself, DPE. We were targeting a generic DPE that's API-driven and data agnostic. And that's very important, because we have a variety of data, different types of data coming in from all these various sources of ingest. And we want to reduce the time to market for the new data sets. So these 2 points are important. However, different data sets do require custom processing and may require different way of storing and archiving. So this DPE needs to be extensible. You need to be able to provide that custom code for those things. It needs to be always on, always flowing, asynchronous, and non-blocking. Mostly it's event-driven and an extremely volatile data, very fast-moving data. So those are the key requirements. And then we were targeting high availability, low latency, and horizontal scalability. So how does the architecture itself looks like? It looks something like this. So we standardize for data coming in on an ingestion API or IAPIs as a RESTful web service. That web service is a very simple web service where providers are going to post the data, or we go and pull the data and then post it there, however we do it. It's going to be very simple. It takes the data and it writes it to a RabbitMQ cluster, and then returns an HTTP 200 OK back to the providers. So its job is done. Data processing engines or different DPEs based on the configuration are the workers that are reading those queues. They are popping the data from the queue, and then they are doing their job. They are processing the data, storing the data, archiving the data. They could be actually posting it to another RabbitMQ cluster, a partner exchange, or they could hand it over to system of record for processing of that data. What about the architecture of DPE itself? There are two major components to that, DPE core and these plugins. DPE core is the only dependency when you are actually deploying a particular DPE, and it's a configuration driven. Think of it like a job orchestrator. Its responsible is to invoking the plugins, these plugins, plugin 1, 2, 3, in sequence, based on the configuration. Plugins are essentially POJOs, where you provide your custom code for process, download, store, and archive. So essentially, DPE comes in, it reads the data from the queue, invokes plugin 1, which might go and download additional information. Data coming in could be just metadata itself, for example. Then plugin 2, it invokes that, and that plugin 2 actually processes that data. Plugin 3 could be writing it to Redis. Plugin 4, which is not here, could be actually archiving it to S3. And we wrote it in Java 1.7, and this is actually running on Amazon Linux. We are going to talk about storage and archive and those things in a minute. Okay, so from AWS perspective, how does that look like? Essentially, this is a single region view, 2 availability zones, of course. Data comes in from publisher. It ends up on an IAPI endpoint, which is essentially a bunch of servers running IAPI code behind an ELB, and one of those picks up and writes it to a RabbitMQ cluster. From RabbitMQ cluster, there is binding in the cluster itself, which, based on the binding, puts it in appropriate queue. And then you have different DPEs working acting as workers for that queue, which are actually taking the data, reading the data, and processing the data based on their ingestion pipeline. And they could be writing it to these stores underneath. OK, so what about the storage itself? So we got the data, and now we need to write it somewhere. We went with an architecture. We knew that the days of standardizing on a database are long over. So we went with a polyglot architecture. We wanted to bring technology team. We wanted to give them flexibility to bring the best store for the job. And not only that, most cost-effective store for the job. Not all data is created equal. So we went with bring your own store kind of environment. And then if you remember, we are targeting extremely high scalability, distribution, as well as very low latency. So we knew we needed a lot of cache. So we made this environment cache-rich. So how does the storage polyglot itself looks like? Something like this. For real-time data and caching, we are relying heavily on Redis. We love Redis a lot, and we have been able to extract sub-millisecond of response time out of Redis. If you think about the forecast data, it naturally falls in a timeline series or time series kind of environment. So Redis allows us to move back and forth in time for that data. Sometimes it's so awesome, it's so freaky that it looks like response came from the future. So we internally call it time machine. So that's Redis. We are relying for real-time data and caching on Redis. For historical weather archive, we are using RYAC, as well as for data migration. We are also very heavy users of Cassandra. We use it for things like gateway data, analytics, heavy users of analytics on Cassandra, and also for things like profile data, also for things like crowdsourced weather data, those kind of things. And then we have a lot of data that we archive. Pretty much all the data except historical weather, we put it in S3. We are very heavy users of S3, and we like it a lot, so we archive it there. Not only that, for static assets, for binary assets like images, videos, we are heavily relying on S3. We put those in S3, and we serve it out from there, of course, CDN frontend. Then from an analytics perspective, lately we have been migrating to this data lake concept, which is Spark A plus whatever storage based. Mostly in our case, it's Spark A plus S3. So we are building our data lake on that. And then, of course, we have relational databases, MySQL and SQL Server, for things like Informatica and Drupal repositories. So what about caching itself? Cache is your friend, but it needs to be used very carefully. So we went with a caching architecture, which is 3-tier. Of course, from the edge, your CDN is going to provide edge caching, as well as edge compute for things like ESIs. But for origin, we are relying heavily on Varnish. That's our origin cache. In fact, all of our architecture, when I'm going to say app servers behind ELB, looks something like this. ELB with a bunch of Varnish instances going to ELB and a bunch of app instances. And we talked about Redis as our app caching. Some of the lessons that we learned in caching is you need to keep this very simple. Don't try to do things like dynamically expiring caches or trying to synchronize the caching or trying to dynamically expire this object or that object, but make sure all the data elements are TTL driven from the ingest itself, from the beginning, and that every step in your chain respect that TTL. Okay, so what about systems of record? Architecture, tenets there, again, were let system designers focus on the job that they are trying to do and let them do that job. Let them pick the best tools and technology for the job. And just make sure that you interface with standard protocols. Both for input and output, use RESTful APIs over HTTP. And then let the layer below and above do its job. So let BPE do the hard work of ingesting the data and normalizing and all those things, and then let the data services do the hard work of distributing it out. Don't put that burden on the system of records itself. And of course, it needs to support both push and pull model for publication. So what does that mean? So first two examples are a pull model. So that's the example of forecast on demand system and currents on demand system, which is observations that exposes that data once it has produced forecast and obs. It exposes that data over RESTful interface. So our data services is simply sitting on top of this, and all the requests are coming through that, proxying through that. And data services is going to try to attempt to actually service that out utilizing its own cache, and in case of cache miss, it's going to forward that request to the system of record underneath. So that's one. But what about things like CMS, content management system, when it's actually there's a publication mechanism involved? So when CMS is ready to publish the data, it actually posts to a endpoint in data services. And that data services then stores it internally in its own store. And in future, it's going to serve it out from there. OK. What about the design of data services itself? Again, RESTful API design, and it needs to be stateless, decoupled. But one of the key things here is this concept of atomic and aggregation services. So what is that? Atomic services are the services that are either provided by system of record, or if we write it in data services at layer itself, it's going to go and read it from the storage layer and return that data. So example is system of record provides 5-day forecast. That's an atomic service. We also have pollen data in our storage, and data services goes and reads it and returns the pollen data. That's another atomic service. But we have a concept of aggregation, which means I can make a single API request asking for multiple data points. I can ask for both pollen as well as forecast data in a single request, and aggregation service is going to go, and it's going to get the data from both these atomic services, aggregate it, and return it out in a single response. This needs to be all key-driven for auth and metering, horizontally scalable, capable of serving billions of requests per day. And one of the key observations is our data lends very well to caching, so let's use it. Let's use the edge. Let's use Varnish. Let's use Redis. So how does that look like? API user comes in, makes a request, and if CDN can serve it out from the edge, it's going to just serve it out from the edge. If not, now API gateway needs to make a determination whether it's a aggregate request or atomic request. And if it is an aggregate request, it actually decomposes it into atomic request, and we use ESIs for those. Those atomic requests are the ones that are going to the origin, so that's OAPI, and that's what it serves those atomic requests. And that's an intelligent mechanism where first it checks for the cache, of course TTL driven, and if it can serve it out from there, it's going to serve it out from there. If not, and the data is stored internally in its storage layer, Redis or RIAC or whatever, in case of a push model, it's going to serve it out from there. But if the data is served from system of records, it's dispatched to those systems, and the request comes from there. And of course, then we cache it again. Okay. So how does the request flow looks like in AWS? Again, sticking with the same model, single region, 2 availability zones. Request comes in, goes to an ELB. From there, it's going to go to OAPI instances, and actually they are Varnish, ELB, Varnish, ELB, OAPI. And request comes from there, and there, if it needs to go to caching, it's going to go to caching. It needs to go to stores, data stores, it's going to read it from the stores. And in case it needs to actually go to the underlying system of records, it's dispatched to those via their ELBs. Because those systems are also running in Amazon, AWS. So what about the push model or the content? Drupal CMS, for example, when it's ready to post the content, in case of binary content like images and videos, it's going to take the asset itself and store it in our static asset pools, which are S3 based. So they are all in S3. And the metadata is actually written to a metadata store. In case of textual data, like articles, everything goes there in the metadata store itself. And then our services are essentially reading it from there. So things like image cut service, things like video distribution services, even MRSS feeds, they are just reading it from there and serving it out. So that's the data services. Okay. So what about authentication, routing, metering, and throttling, all these kind of things? This is all the job of gateway. Some of the key requirements for us for gateway were this gateway needs to be not just CDN aware, but CDN driven. And we are going to talk about what that means in a minute. Also, remember that pesky 25 millisecond latency target, it's still with us. So we cannot add a lot of latency to this. So we looked at quite a few solutions out there, and we could not find something that satisfies, so we rolled our own. And this is how it looks like. API user comes in, makes a request. CDN itself checks for authorization by doing a look aside. So what does that mean? We wrote a quick service, a quick authentication service, quick response service, which is essentially a very simple service that reads from Redis and in sub-millisecond response times returns a yes or no, authorized or not. And then CDN, once if it is yes, it proceeds with its normal caching and origin routing and all those kind of things. But the source of authentication truth is actually sitting in Cassandra database. That's where the keys are. That's where metering and all those things happen. And they all happen in the background. So from there, they are simply synchronized to Redis. So we actually sacrifice some real-time throttling and metering for low latency. Okay. So far, we have been predominantly talking about a single-way data flow from the weather channel itself to our users. But our users are actually doing a lot of things on the platforms itself, so, and hence they are generating events. How do we handle that? We use Amazon SQS for that. Initially, we thought of rolling our own by using maybe some queue and web service in front of it, but then we realized SQS actually does it, so let's just use that. That's what we are using. So events are coming in, they go in SQS, and then Spark Streaming actually can read it and do stream processing from there, but we have our own custom ingestion pipeline, which takes it from there and puts it in our data lake. For batch files, for example, Google DFP, all those kind of files or third-party files may come from S3 or from whatever batch source. We use Informatica ETL for that. So we read it from there, and that also goes in our data lake. Our data lake is essentially S3-based, and it has long-term raw storage, so raw files also go there. And then we use EMR and all those kind of abilities to create Parquet files and put that in S3. We are still heavy users of Cassandra and Spark Cassandra combination for short-term storage and big data processing, but we actually like the concept of data lake a lot. Then we have Spark SQL for data access, and then for visualization and dashboard, we use things like ClickView and ClickSense and ClickView and all those things sitting in front of it. So that's how our events and analytics look like. So let's put it all together and see how the entire stack looks like. Looks something like this. We are across all 4 global regions. Well, we are across 4 global regions. And we have the entire data stack running in these 4 regions, from ingestion all the way to distribution. So we ingest data in all the regions, in all these 4 regions. We process it there. We actually cache it and store it and all those things and distribute it out from there. Of course, due to the limitation of databases and limitation of certain other things, cost included, you can't really do those things all the time. So we have some remote ingestion and replication going on as well. But by and large, we like to stick with this environment where we actually run the entire thing in each region. We have another region dedicated for configuration management, monitoring, and automation for things like Puppet and Chef and Zabbix and all those kind of things. OK, so that was the plan. So that's the architecture. And we had a roadmap based on that. And we were building different components. Project was moving along. And then this happened. We were served a curveball. The moment our forecast on demand system was ready, we used that to actually strike a deal with a major mobile phone company to ship the new APIs for them, for that weather data. And due to the scale of that, we were targeting 25 billion requests per day. And time to market for this was 3 months. We had to deliver it in 3 months. So after some celebration and heavy drinking, and also actually throwing up, though not necessarily sure in which order for all of us, we sat down to do it. And this is what we found. That's where our decisions for loosely coupled architecture, atomic aggregation services, and the scale of AWS really shined. Because we have atomic services ready coming from forecast on demand system. We have to write a custom aggregate for that vendor, for that partner. So we wrote that. And then we have to scale that to handle those 25 billion requests. All this in a matter of 3 months. So we wrote that, and then we launched ourselves into this cycle. Load test, tune, destructive test, fix. And we caused a lot of things. We caused VPC NAT saturation, DNS server saturation, so we had to figure out the correct sizing. We had to figure out the correct instant types and sizes for every layer or every component in that layer, for Redis, for IAPIs, for OAPI servers, for varnishes, for all of those. And then we ran into OS kernel limits as well, so we had to do kernel parameter tuning. We ran into issues with compression and decompression, so we had to actually fine-tune that as well. And then we also did, to make our environment very resilient, we did this chaos monkey philosophy, destructive test and fix. We brought down instances, availability zones, regions. We corrupted caches. We brought down databases, or the shards for the databases and caches. And we fixed those things. We figured out ways around it. So one of the key takeaway here is this step is very, very important. It's extremely important as the development itself. But it takes time to figure this all out. So make sure that you budget time and resources for both load and destructive testing. With that, I'll hand it over to Raul to provide some AWS insights.
Thank you, Jagmeet. Good morning, everyone. Also for you. Good morning. Well, my name is Raul Frias. I'm a solutions architect for Amazon Web Services. I've been in AWS for 2 years, and actually this is my second reinvent, and really excited about it. And so building this type of architecture, so just like Jagmeet mentioned, takes a lot of time and effort to build them out, and it's something that you need to budget for. And one of the things that the weather company had already built was a decoupled architecture, and they just needed to focus on scaling the different layers of that architecture. And when some of you may find yourselves with similar challenges, just as a weather company and Jagmeet, where you have a very small amount of time and limited set of resources in people and tools, one of the things that you could build out and streamline building this kind of applications or architectures is kind of leverage the managed services. And so I'm not here to tell you about all these managed services. I'm actually here to talk to you when might be a good fit or may not be a good fit for your different application needs. And one of the things that we see with these managed services is customers using them in one of two different paths. One path, customers start building brand new architectures, brand new applications, and they're leveraging these managed services from day one, and they love them, they hook them, they're hooked to them, and sometimes they even grow out of them. And the other path that we usually see is customers managing the AWS basically as an infrastructure platform and managing their IT resources basically the same way they've done it before, like in the old ways, like the dark ages before the cloud. And after some adoption, we usually see them now starting to leverage these managed services and do this undifferentiated heavy lifting that you probably heard about, and you're going to hear about it a lot in AWS today. So I'm not going to cover all of this managed services. There's going to be sessions that specialize in all of them. I'm just going to cover some of this and how we match them to some of the services that the weather company has done and how you can streamline building some architectures like this. So first of all, if you recall the storage layer from the weather company where they're basically using a lot of storages and a lot of databases out there. They did mention for relational database point of view, they're using MySQL and Microsoft SQL Server. So one of the options that you have here is we have a managed service for database service, AWS RDS, Relational Database Service. When you would like to use an RDS solution versus an EC2 managed relational database, right? So two main factors here, performance and size usually are some of the factors that your decision will be made from. You can see from the table on the deck, performance and terabyte sizes depending on the engines. We already this is already outdated, right? We already have MariaDB now also as an RDS choice. But when you start reaching these limits, these maximum limits, it's probably a good sign that you're starting to grow out of these services, and you should go out into an EC2-based relational database. Also, licensing, bring your own license, or if you're interested in on-demand licensing, RDS offers both options, and there's a couple of options for SQL Server also regarding on-demand licensing. Replication. RDS manages basic replication in multi-ACs, master-slave replication. If you're interested in having more advanced or complex replication schemes, then you should definitely build your own the EC2-based solution. And of course, the differentiated heavy lifting, right? The backups, the updates, installing, and everything else. Also, the weather company, Jagmeet mentioned a lot of options out there from NoSQL, right? And so many customers are, we're seeing a lot of traction with the NoSQL database space, and this is not something that's going to go away anytime soon. There's a lot of options out there, and the questions with our customers usually go around like, which would be the best NoSQL option for me out there? So I won't cover all the options that are out there. I'm just going to cover this two and a managed version like from Amazon, and instead of just going through to the ones that the weather company is already using, right? So first of all these NoSQL databases share some common patterns. That's schema-less. They don't have any kind of relational foreign keys to relate different tables. And indexing is a very important thing that that you should consider from the beginning, right? There's no afterthought in the indexing. And so if you care about the performance of your database, you really need to analyze your query patterns for your performance in NoSQL. So when does these ones apply on some of the challenges? First of all, Cassandra. If write performance is a concern for you, this is one where this NoSQL database really shines out. Also, they have a very good native multi-region, multi-AC replication with their own nomenclature. Also, there's commercial options out there with DataStax offers solutions, services and support for commercial options out there with a huge ecosystem. And some of the challenges that customers face when building this kind of non-managed solutions like Cassandra, and this is also shared with RIAC in this deck, repartitioning, right? So when you want to handle scaling, scale out your own your NoSQL database, this is not an automatic process. This is a manual process that you need to take some stuff into consideration. And this consideration sometimes will lead into over-provisioning, EBS, and EC2 resources. All the operational burden, installing, configuring, setting it up, it's still a manual process that you need to do yourself. And also, if you're going to do some kind of multi-region or multi-AC replication, and this applies to both RIAC and Cassandra too, you're going to incur in data transfer costs, right? So the second option, RIAC, also used a lot by the weather company. This one really shines a lot in all the availability space, right? Based on the Amazon paper, there's zero downtime design for that. They also shine really good in the cross-region replication with their own nomenclature. They face similar challenges in this space, very similar challenges to what Cassandra deployments are. Repartitioning, scaling in, it's not automatic. You need to you need to have some considerations regarding that, and the same operational and data transfer cost. And DynamoDB, just to put it out there, I'm not going to sell you DynamoDB. Many of you already know it's effortless scaling. You just need to put the write and read throughputs. Effortless scaling, and the one thing is about this is also constantly evolving, right? DynamoDB. So like you just came from the keynote, and you probably see that we like to make announcements a lot in this company. So this is constantly changing, but some of you may be interested in when this may not be the best fit for you, right? So item size right now from DynamoDB, right now it sits at 400 kilobytes per item. If your items in NoSQL are higher than that, this may not be the best fit for your application. And also cross-region replication with DynamoDB. Last year we launched DynamoDB streams, but there's still some manual procedures that you need to do and the work that you need to do and apply. So we're still constantly evolving, and I would just tell you to stay tuned. This probably be something that we're working on. On the other one, recalling the data distribution engine, or the data processing engine from the weather company, as you may recall from Jagmeet's stack, this layer was basically in charge of the whole scaling, ingesting the data, and processing this data. And there's some services that you could use to streamline this building of a very similar data processing engine with two different technologies, right? So first of all, streaming storage. Right? The whole point of streaming storage is we could decouple producers from the consumer so that we can scale them independently. You have a temporary buffer of your data, and you can serialize all your information that you're putting in the stream storage, and you can kind of do like a streaming map reduce from your client side. And this is something that we usually see with two tools, right? The managed option from AWS, Amazon Kinesis, and there's Apache Kafka, also used by a lot of our customers. And they both have a lot of similarities, multiple consumers, the ordering of records, low latency, highly durable, scalable, and available. So the interesting thing, the differences, right? Record lifetime and record size. Most of the difference rely on that. Record lifetime in Amazon Kinesis is set in 24 hours. It's not configurable. Whereas in Kafka, you can configure that. Also, the record size. Right now in Kinesis, it sits at maximum 1 megabyte per record. At GA that was launched, it was in the kilobytes of size. It now sits in 1 megabyte. Kafka, this is completely configurable, right? Of course, Kinesis is fully managed. There's no EC2 instances that you need to launch and configure and handle. So this is the first component, like the streaming storage. And here, like giving it like an AWS style to this data processing engine from the weather company. And this is something that we're really excited to show it to the weather company and to other customers. That's how about imagining a serverless approach to building this type of ingestion and processing layer, right? So here comes Lambda, right? Our code as a service, where you basically give us your code, your application, and we run it for you. There's no EC2 instances, there's no servers to manage out there. And this is how we would imagine this. Like having Amazon Kinesis, managing all your streaming storage from your different data inputs, and having Lambda take action on them and process it, and actually putting it afterwards in a persistent storage. Amazon RDS, S3, Redshift, your own EC2-based relational or non-relational databases, right? So with that, I hope this AWS quick AWS insights give you some practical ways to build architectures like this faster and reduce your burden. And I'm going to leave back to Jagmeet so that he can talk to you about the future. Thank you.
Thank you, Raul. OK, so how are we evolving the architecture that you saw earlier? Of course, we want to stick with the things that work for us. And we want to try to make an attempt to fix our pain points. So let's take that approach and see how we are evolving it. To begin with, we want to stick with the layered architecture and loose coupling, interface via RESTful APIs. We are going to stick with that concept. That concept has worked well for us, and we are going to stick with that. So we are still going to have GTM, CDN, and all those kind of things. We are still going to have edge caching and edge compute and edge side includes. We are still going to have common services layer. We are going to extend that actually to do for multiple more things, router and controller. And we are going to still stick with our auth and metering. We are still going to stick with our storage polyglot. However, the problems that we are suffering are in these two layers, DPE below and data services above. And that's actually the pain of monolithic architecture. So enter microservices. So we are planning to evolve this architecture with a microservices approach. For data services, we are planning to actually break it down into microservices. That's already in progress. So microservices are going to be centered around data points or different data types or cluster of those services, for example, for location, for aggregation, for forecast and lifestyle and so on. And these microservices are also going to bring in another important part to this layer, and that's the language polyglot. So we are going to give technology team flexibility to write even the services in different language or language of their choice. So they can write it in Scala, Clojure, Java, Node.js, whatever they want. We are going to take the same approach, or similar approach, I should say, to micro DPE, try to break it down, DPE, that monolithic DPE, into micro DPEs, try to bring a services approach, microservices approach to that. And we are going to do that by doing things like Avro, Thrift, and protobufs. So that's what we are planning to do, microservices type of model for ingest with Avro, Thrift, and protobuf. So we are going to attempt to break it down. For queuing, we are already using SQS for events, and we are going to extend that usage. So the plan is to actually use it more and more. For streaming, we are looking at Apache Kafka. That's what we are looking at. And then for distribution, microservices and language polyglot, I already talked about that. And then we are going to actually build a service discovery engine around that. For storage, our plan is to look into Aurora, Amazon Aurora, and RDS and all those things for relational databases that we have for Drupal and Informatica and all those things. So we're going to stick with bring your own store concept there as well. And for analytics, we are going to keep on building on our data lake with Parquet and S3 combination. We are going to rely on Spark, but we are also looking at Amazon EMR to actually produce those Parquet files for us. So wrapping it up, what are the key takeaways here? To begin with, have an architectural blueprint. Think through your layers. And then keep those layers loosely coupled or decoupled. Communication for these layers, standardize those with a standard protocol, like RESTful interface over HTTP. And then try to keep your architectural plan technology agnostic. Give your technology team flexibility to pick the tools or stores of their choice or language of their choice, storage polyglot and language polyglot. Then if there was one thing I could tell myself 3 years back when we actually got into this effort, that's this: be aware of the monoliths. And that's what we are trying to do with microservices. Another key learning, keep caching architecture simple, make it TTL driven. And of course, we touched on always, always, always budget for load testing and destructive testing. With that, thank you very much. And that's it.
It was smart. Yeah.